You know, my house is literally like an architect.
Okay.
During lab. You didn't even
Take my keyboard off here. Let's try this again. There it goes. The computer took a little while to wake up this morning. My apologies on that. Welcome to lecture 6 and our last lecture before our long weekend, right? Because we don't have class on Monday. How did the concentrated moment assignment go? I imagine that the hardest part wasn't the concentrated moments; it was in distributed loads. So, did that go well? Okay, I'll take that as we hope it went well.
I'm gonna lie, if you wouldn't have said anything about like putting our notations down, I wouldn't have an issue. I didn't put nothing on there in the second problem. Dude, I had to do the whole thing over again. I mean, I completely had to restart because I didn't know what I was looking at.
Alright.
But, you know, I guess you were just like on my shoulder.
I'm not. You've had me for class before. Have I ever been one of those professors that I enjoy the misery of my students?
I think so.
You think so?
Yeah.
I think you enjoy being right. I think there's a little sense of hell yeah, I was right.
I appreciate the science. I like the, when we start doing shear and moment diagrams, you'll sort of see there's sort of a clarity in the problems because there's a way in which they check themselves. It's kind of cool, but we'll get to that later. Okay, so homework 2.4 is assigned today. It is due Wednesday, but it's just, I think, one problem, and it's not any more or less work than the other assignments. Like I'm not saying, ooh, I've got 5 days, let's make the homework long. I'm not doing that. It's pretty comparable. Today is our last lecture on purely devoted to support reactions. Now, to be clear, we're going to be solving support reactions throughout this semester, so that's going to be inherently true. But this is our last lecture that is devoted solely to exploring how to compute support reactions. So from here on out, after today, when we start doing stress analyses and shear and moment diagrams and so on and so forth, we are going to be solving for support reactions, or in some cases they may be given, but there's going to be an understanding you know how to do it. This is definitely a class that sort of builds on itself in terms of the content. Okay, did everybody get the code? Everybody get the code? All right. So, all right, let's get into support reactions. Our last lecture, and so today we're probably handling our most complicated type of problem, and that is any type of structure that has an internal release. The reason why they are the most challenging is because if you remember the equation for classifying a structure, so we've been solving problems up until now that have 3 reactions. Well, if you throw in an internal release, you have to throw another reaction in order to get an I value of 0. So anytime you start thinking about problems that have internal releases, we're talking about problems that have 4 reactions or 5 reactions or so on and so forth. So there's just more to do, okay? That's not to say that any of this stuff is different. I mean, we're all handling it the same way. Things like concentrated loads, distributed loads, concentrated moments, all that, we're all handling that the same way, and we're handling the boundary conditions the same way. Again, the only thing that changes is the inclusion of these internal releases. Now, we've talked about internal releases before. From a modeling standpoint, from a mathematical standpoint, internal releases are essentially points on the structure for which you know the internal response. The most common internal release is a hinge, okay? And a hinge is a known point on the structure where the internal moment is 0. Hinges cannot resist moment. You apply a moment to a structure where there is a hinge, it will freely rotate, okay? So our fourth equation, if it were. So we're going to have sum of forces in the x direction, sum of forces in the y direction. We're going to have sum of moments about any arbitrary point where the whole structure is 0, but we're also going to have a fourth equation when we have hinges, and that is that the sum of the internal moments at that point is 0. Okay? Now, in order to deal with internal releases, we got to break out the secret weapon of structural engineering, which is a samurai sword or lightsaber if you happen to be a sci-fi fan. I think we've talked about this before in here, which is that if I'm sitting on a table, right, I'm applying force to the structure, and if somebody comes on the other side of this table with a samurai sword or lightsaber and you cut through the table, I'm falling to the ground, right? And the reason why is because you have removed from the structure the ability to resist these internal responses at that point, okay? The idea of cutting a section, or that tool, that analytical tool of cutting a section, it's one of those powerful tools that we have, because what we can do is use that to investigate the internal response at a given point. We're going to be cutting sections throughout this semester for a variety of reasons. Things like validating the answers that we compute. Sometimes we'll need to cut sections in order to be able to just analyze the structure. We'll cut sections to determine internal forces, internal shears, internal moments, etc. We'll also cut sections in order to write equations for structure, specifically to try and graph moment as a function of x, or graph shear as a function of x. And we do need those equations later because whenever we have moment functions, we can use those moment functions to compute deflections. In other words, if I have a beam and I apply loads to it, the beam deforms. Moment functions are necessary in order to determine how much it's deforming, okay? And so that we'll get to that later, but the ability or the idea of cutting a section is a very useful tool, and you're going to see that today. So what happens when you cut a section? Okay, so again, if I'm sitting on a table and somebody cuts a section through an arbitrary point on the table, what happens is I fall down because I have released from the structure the ability to resist that internal response. Now I propose if you cut a section through an arbitrary point in a structure, you're going to get at most 3 unknowns, okay? You're going to get an unknown force in the x direction, an unknown force in the y direction, and an unknown moment, right? Sort of lines up with what we've been talking about before, okay? Now, if you cut a section, if you break out the samurai sword or lightsaber, what you're doing is you are separating the structure into 2 pieces. Whatever you cut that's on the left and whatever's on the right, okay? From an equilibrium standpoint and from an analysis standpoint, it doesn't really matter which side that you look at. You're going to get equal magnitudes on either side, but they're going to be in opposite directions. Sometimes that's a little bit hard to wrap your head around, so let me give you a basic example. Okay, so let's say Mr. Sindeldecker's holding one end of a rope and I'm holding the other end. Okay, and let's say that our goal is to apply a 20-pound tensile force inside the rope, okay? So we want to put 20 pounds of tension in the rope, okay? Which way are you going to pull? Towards me. And which way am I going to pull? Towards me, right? So we are going to be pulling in equal magnitudes, but opposite directions, right? But we're both doing the same thing. Does that make sense? So if I cut a section and I look, let's say, to the left, I'm saying that a tensile force is yanking away from the member, and here I'm saying the tensile force is yanking away from the member. So it's like, well, why is P pointing to the right over here and pointing to the left over here? Because they're both doing the same thing. They're both applying a tensile force to the member in question. Does that make sense? And so whether I'm looking at horizontal forces being right over here and left over here, or shears being down here and up here, or moments being this way and that way, I'm just showing equal magnitude in opposite direction, okay? What I have drawn here, and this isn't really going to matter for today, but this is going to be important later. What I've drawn here, I've drawn these arrows in very specific directions because they correspond to the positive sign convention that we're going to be using this entire semester. For today, not really going to matter all that much, but these directions were not drawn arbitrarily. We'll get to that later. Okay. What I really want to focus on is the difference between this and this. Okay. I propose that if you cut a section through some random point in the structure, you're going to get 3 possible unknowns. But if you cut a section through a hinge, you're going to get 2 unknowns, okay? You're going to get an unknown force in the x direction and an unknown force in the y, but no moment, okay? Why no moment? Because it's a hinge. Hinges cannot resist moment, okay? They cannot develop an internal response, right? Go back to the issue of me sitting on the table. If I sit on the table and you cut a section and I fall down, the reason I fall down is because at that point there was an unknown force in the x direction, there was an unknown force in the y direction, and there was an unknown moment at an arbitrary point because this is a solid table. But if I cut a section through a hinge, there is no unknown moment, okay? There is no unknown moment because the hinge can't resist that. It can't hold me up, from a moment perspective right there at that point. When we start drawing shear and moment diagrams and we start looking at beams with internal hinges, we're going to see that the moment diagram crosses 0 right there where the hinge is. It's going to be a way of checking that the math that we've been doing is correct. Okay? Does that make sense? Don't worry. We're going to have plenty of examples on this, so don't worry. All right. Here is sort of a breakdown of the sign convention. It's not really going to matter today, but we are going to be using this quite a bit later on in the semester. For example, when we write shear and moment diagram equations, this is the positive sign convention for shear, this is the positive sign convention for moment. We traditionally consider positive axial forces to be in tension. So if I have a member and I'm yanking on it, we consider it a positive sign convention. If I push on it, we consider it a negative sign convention. The main reason why is if you take a member and you yank on it, you are increasing its length. You're making it longer. So that's why we consider tensile forces positive. Some software programs don't. They consider compression positive because they're mostly looking at like beam and column design. But I just throw that out there just for reference. Again, won't really matter a whole lot today, but it'll matter a lot later on throughout the semester. So far, so good? All right, let's do a fun problem. Okay, so I have here a, here, let me pull up the notebook here so it's a little clearer. Okay, so this is a problem we're going to look at. There's a lot going on here. I have like a 2-span beam. I've got a distributed load here, a point load here, a triangular load here. I got a distributed load here. I got all sorts of fun stuff. One other thing worth mentioning is that I've got more than 2 support reactions. One of the things I've done on my graphics is that whenever I have a beam and I've got this little white circle right there that represents a hinge, the textbook sometimes will just point and say that is a hinge, but a lot of times on my slides or on my homeworks and exams, that's what I'll do is I'll just put a little circle there to indicate the presence of a hinge. So we're going to compute support reactions for this beam. Okay, and again, notice we've got a lot of them. Okay, we've got how many reactions? 1, 2, 3, and 4. Right? Make sense? All right, so a couple things I'm going to do. The first thing I'm going to do is I'm going to look at these support reactions. I'm going to, for the sake of simplicity, assume that they all act upward. It's possible one of these assumptions is wrong, but if I assume they all act upward and one gets negative, then it's sort of easy to figure out which direction it is. And in fact, this is what software programs do. It just assumes they all act upward, and if it's negative, it's downward. So we'll call this AY, BY, CY. Okay. I'm also going to go ahead and assume this reaction here. But can anybody tell me what's going on with that AX reaction? It's 0 because there are no horizontal forces. So let's go ahead and handle that right now. Let's just go ahead and deal with that. We know that AX equals 0. Okay. All right. Let's start dealing with our loads that we have on the beam. All right, so we have 2 kips per foot acting over a distance of 15 feet. So I'm going to collapse that into a single point load of 30 kips. And from the left support, what is that distance? There we go. Don't forget we also have this concentrated load right there of 14 kips. Okay. What about here? So we have a triangular load. Okay. So we have a triangular load that is that goes up to a magnitude of 4 kips per feet over a distance of 15 feet. So what is that collapse into? What's that point load?
30 kips.
30 kips. It's not 60, right? It's easy to go 4 times 15 is 60, but it's a triangle. Divide that by 2. And for simplicity, what's that distance? 5 foot. Okay, and lastly, we have 1.2 kips per foot over a distance of 15 feet. What is 1.2 times 15 going to be? 18. So collapse that. And then we'll say, I don't know, from that end, what's it going to be? Okay. Let's just take a sec, make sure we're all comfortable with that. Is that good? Everybody good? Okay. All right, let me ask you a question. Well, I'll tell you what, let's do this. Let's assume that this is a problem like any other, okay? Let's just ignore everything I said about cutting a section. Let's ignore everything I said about internal releases and hinges and all that. If I hadn't talked about that at all today, in the slightest, what would be the first thing that you would do to try and start solving this problem? Some moments a day, right? Let's do that. Let's see what happens, okay? So let's see what we get. So let's some moments a day. Let's just see what happens. Okay. All right. So do we have to consider AX and AY? All right, so walk me through this. What do we've got? 30 times what? 14 times what? 15. 30 times what? 35. 15 to 35. And 18 times what? What was that? 15, 30, 45. What is that? 52.5? All that's over here on this side, right? So let's just write that out. So okay. Now what do I have left over? I've got, so I handled all the loads. Do I need to consider BY at a moment arm of? And do I need to consider CY at a moment arm of? 60. And that's going to be going the other way, right? So I've got BY and CY. So, okay. All right, somebody help me with this. What am I going to get in this column? We're going to get that times that, plus that times that, plus that times that, plus that times that. What is that? I know it's Friday. I know we got a 3-day weekend coming up, but I'm going to make you
What was that last number beside of 18?
52.5. No problem. 2430. Do I have a second on that?
Yeah.
Okay, so 2430 foot kips equals BY times 30 plus CY times 60. Okay? So, now what? What's BY? What's CY? You don't know, do you? I mean, so before, what we would do is we'd do all this and we'd get like BY equals 20 or CY equals 57 or whatever. We didn't get that, right? We've got two unknowns, right? So granted, I'm not saying this line here isn't useful. It's very useful, but it doesn't give us an answer, right? It's just an equation that relates a couple of our unknowns. Okay, so here's what I'm going to do. Okay, I'm going to box this. I'm going to call this equation 1, and I'm just going to keep it in the back of my head. I can't do anything with it. I mean, like, I'm going to do something with it later, but this equation does not independently tell us what is BY or what is CY. It just tells us how they compare to one another. That if I take whatever BY is times 30 and whatever CY is times 60 and add them up, I'll get that. So maybe a way of thinking about it is if I knew what BY was, like if I had some magic tool to figure out what BY was, I could plug it in and solve for CY. Does that make sense? I could do that. Okay. All right. What about what about summing forces in the y direction? Maybe that'll work. Maybe, I summed moments and it didn't help me. Maybe summing forces in the y direction. I know that'll help. Okay? Let's do that. Let's sum forces in the y direction. Okay. What about summing forces in the y direction? What do I have going up? I've got AY, BY, and CY. What do I have going down? 30, 14, 30, 18. I'm getting a little nervous. I don't think this one's going to help me out either. So let's see if I can do it. 14 and 18, that's 32. So 30, 30, and 32 is 92. So okay. That doesn't help me either. I'm not saying it's not a useful fact, but it doesn't help me directly to solve for one of these unknowns right now. Okay? So how am I going to solve for these unknowns? How am I going to figure out exactly what is AY, what is BY, what is CY? How am I going to do that? I'm going to break out my secret weapon of structural engineering, the samurai sword or the lightsaber. Okay? Now, I am going to samurai sword or lightsaber through a very specific point. Can anybody guess what point that's going to be? The hinge, right? Okay, so what I kind of do is I'll say, okay, let's cut right here. And so the way that I like to do it is, you know how like on a blueprint or a CAD drawing, you'll have like section 1-1 or section 2-2. So that's what I do is I'll say section 1-1. Okay, now let's reason through this. Okay, the structure does not care how we do this, but that doesn't mean we have to make our own job harder. Okay, whenever you cut a section, the structure does not care whether you look at the left side of the cut or the right side of the cut, right? In the end, the internal forces at this point are the same whether you consider the left half of the structure or the right half of the structure. Whenever you cut a section, you're cutting a structure into two pieces, right? And you investigate the equilibrium of each individual piece. Now, like I said, while the structure doesn't care, that doesn't mean we have to make the problem harder. So if I were to look at this structure and I cut a section, would you choose to look to the left or would you choose to look to the right?
Right.
The right, okay? There are three reasons, I guess, why I would look to the right. For one, just look at the structure. It just seems easier to look to the right. But why does it seem easier to look to the right? Well, for one, there are less known forces to deal with. On the left, I've got this triangular load. There's all this hullabaloo on the left. Whereas on the right, all I have is that distributed load. It's a lot less forces to deal with. But a more apt reason, really the real reason to look to the right are the unknowns. How many vertical unknowns do I have to the left? How many vertical unknowns do I have to the right? I can isolate that unknown by looking to the right. So that's the real reason you want to look to the right, is because there's only one unknown. Okay? So what I'm going to do is I'm going to say, okay, I can do better than that. So we're going to cut a section at the hinge. And we're going to look to the right. Okay? So, here's what I'm going to do. Okay? Here's the beam. I am samurai sorting, looking to the right. So I'm basically going to redraw everything on the structure that's to the right of that cut. Okay? So what does it look like? Well, it looks something about like this. I've got this. I have a distributed load right here. That's where I did the cut. And I have a roller. Right? That's what I know from the right side. Okay, let's start adding some values, some data. This is 1.2 kips per foot. I have a reaction here, which I assumed upward. We'll call that CY, just like we did before. Remind me, what is this distance right here? 15 foot. Okay. And then I collapsed that, or I can collapse that into a single point load of 18 kips. From where I cut the section, that is the distance of?
7.
Okay. All right. Everybody with me so far? Now, I cut a section through a hinge, okay? So if I cut a section through a hinge, there is an unknown force in the x direction and an unknown force in the y direction. I'm going to go ahead and draw them just to say that they're there, but they don't really matter in terms of if I get the directions right. The values themselves don't really matter in terms of computing the support reactions, and you'll understand why here in a bit. Okay, so now I want you to look at what you see here as if this was a separate structural analysis problem all on its own. Here's the problem. I'm asking you to find the reaction at C. How would you do that? At this point right here. So at the hinge, right? So here's how I'll write it. I'll say, let some moments at the hinge, and here's what I'll do. Some moments at the hinge looking to the right. So you see what I did? I said some moments at the hinge, and then I have an arrow over here indicating that the part of the structure that I looked at was to the right. So, tell me what to write. Tell me what do I do? If I'm summing moments here, do I have to consider fx and fy? No, because they pass through the hinge, right? So it doesn't really matter what the values are, right? So, what do I do? Tell me what to write. 18 times
2.5.
Well, not 2.5, 7.5 on the left side of the table, right?
Yeah.
And then what goes on the right side?
CY times 15.
There we go. So 18 times 7.5, that's 135. So therefore, I get that, right? Which, I mean, I kind of did some of that math in my head, because if it's 18 times 7.5 has got to equal something times 15, this is, these, you know, this is double that, so that's got to be half that. So, does that make sense? So, we've got one of our support reactions. Here's one of our support reactions. So, tell me what to do. Now what?
Plug it in for the by CY equation.
Equation 1, right? What was equation 1? Right here. Equation 1 says by times 30 plus cy times 60 equals 2430. I said we can't solve for a reaction, but if we magically knew what one of those values were, we could plug it in and solve for the other. Well, by golly gosh gee, we now know what one of those values are, right? We know it's 9 kips. So what I can do is I can say, okay, let's go back to equation 1. I'm going to move that up just a little bit. Okay. So equation 1 was by, bless you. Right? That was equation 1. By times 30 plus cy times 60 is 2430. Well, now we know what cy is. There you go. Right? So, can somebody, is anybody able to solve this and just tell me what by is? So, one of the advantages of just assuming all of the reactions are upward is that when you get to scenarios like this, if the reactions are negative, for one, you know they're downward, but B, because all of the reactions are assumed upwards, just start plugging negative values in. Like, for example, what if we had done all this and we got cy was 9 kips acting downward? Instead of having to like redo the equation, just plug in -9. You see what I mean? Because we've already accounted for that by just assuming they're all upwards. So that's one value there. All right. So now what do I do?
Okay, put those into equation 2.
There we go. So now we have equation 2.
Let's go.
So it really kind of is. And I'm going to make a few comments about that here in a second. So this is 63 kips plus this is 9 kips is 92 kips. So 63 plus 9 is 72, right? So 72 off of 92 is 20. So AY is that. So what is my answer? Okay. How many answers do I have? 4. Yeah, we forgot one. What was the one that we forget? AX equals 0. That one's an answer, right? Don't forget that one.
I'm not going to be able to understand this later.
You've got to do it. This is one of those learn by doing things.
I need my notebook.
Oh. So Mr. Coupler, you said you think I just like being right. Here's the honest truth. When we start doing like shear and moment diagrams, there's gonna be something that happens that's like really neat, right? So you do this, right? And you get these numbers. The shear and moment diagram will verify that those numbers are right. Because if these numbers are truly in fact the correct numbers, then when you draw your shear diagram, it will start and end at 0. When you draw your moment diagram, it will start and end at 0. The problem has a way of self-verifying that it's correct. I find that really neat. I do. I still to this day find it really cool. Like when you, because if you look at the shear and moment diagram for this structure, it will look wild, but it will be right. So.
But you still love being right.
I like the puzzle.
So you're telling me that when you get done, you do all this, excuse me, you do all this, and you just go, man, I love the theory, man, I love. You don't sit there like, hell yeah, buddy. You're like,
Well,
stoked you're right.
I don't think I'm gonna. Well, I don't think I'm gonna do a problem and stand up. Let's go. but I do enjoy it. I mean, if anybody here enjoys like puzzles, like this is kind of a puzzle. So.
Well, I don't know what puzzle I get in Diffie Q, but I do backflips when I ride.
That's real.
Differential equations.
You said that like you missed it there, I'm sure.
First order, second order. I enjoyed my Diffie Q class. I did not really enjoy when I think it was Calc 2. I didn't really like Calc 2, but that's me. I like it. Like I felt like when I went to grad school, I started like really using it. Like when I took the class I took on earthquake engineering, and we actually started using it, I gained a much deeper respect for it. So.
So say I will get mad if people are getting mad at math.
I know you are. I know you are.
So when in the field, like when in your career did you actually like start implementing the stuff that we like Calc 3, like
So-
we'll sit down there, all right, now I
It-
understand it.
In all honesty, we are going to be using calculus in here for deflection computations. We are going to use it. When I really started heavily using it was things like vibrations and beam and plate analyses. So like earthquake engineering is like when you really use it quite a bit. So.
So if you were to, bridge engineers are the ones that like do this, right?
Bridge, buildings, structural engineers, yeah. So, but yeah, like for any time you're dealing with vibrations, it does start to get pretty math heavy, but it's pretty necessary. I mean, you have to understand the frequency of a structure so that you can design it so it won't fall down during an earthquake. So, yes, yes, sir.
The first moment that you took to see why did we do that? Because if I'm thinking about the hinge, right? It's
Yeah.
allowed to rotate, right?
Yes.
So in my mind, I'm thinking, if I put a force down on that, it's gonna.
So here's what I'm saying. That's a fair point. Here's what I'm saying. Okay. So if I cut, let's take the door here, right? So the door can freely rotate, right? If I apply a force here and I do that, it freely rotates, right? So here's what I am saying. Here's what I'm saying. What's going on? So let's go to this diagram, right? Okay. What I'm saying is I represent the red 18 kip force, right? So I'm here and the structure would freely rotate, right? Well, let's say Mr. Allen was here. Mr. Allen, let's say he's standing back here. Mr. Allen represents the CY reaction, right? And so if I do this and he pushes this way, right? What I'm saying is that the total sum of moments is 0, right? And I'm allowed to sum moments at the hinge because the hinge carries no internal moment, okay? So what I'm saying is the moment that I'm applying has to be counteracted by the moment that he's generating. And
Still just in that one piece, right?
just in that one piece.
So why did we take the moment for the whole length?
You're talking about this one?
Yes.
Because I used this equation to find By. Here's what I'm saying. How many unknowns did the entire structure have? 4, right? How many known equations of equilibrium did I have? 4. I had the sum of forces in the x direction, which I used directly to find AX, right? I had the sum of forces in the y direction, which gave me this equation. I had the sum of moments about the entire structure, which gave me this equation. Too many unknowns without this fact, right? This fact here, this sum of moments at the hinge, is what yielded CY. Take CY, plug it into here to get BY, takes these two, plug it into here to get AY.
Yeah.
That's what I'm saying.
It's the 60 foot causing a turning of the other beam.
Yeah. So in the end, what I'm saying is, independent of whether that hinge is there or not, the entire structure can't rotate. The entire structure has to sit still. Does that make sense?
I'll have to think about it.
I know if it's your first time doing it. Let's put it like this: when we start looking at truss analysis, okay, when we start looking at truss analysis and we start looking at the method of joints, we will use sum of forces in the x direction, sum of forces in the y direction, sum of moments to solve for the reactions of the entire structure. But to figure out the internal forces in all the members, we'll look at the equilibrium of each joint. Because not only does the entire structure has to be in equilibrium, each individual joint does too. You see what I mean? The whole structure has to be balanced out. Does that make sense to everybody else?
I think I understand.
Okay. Don't worry, we'll get, the more we do this, I think the better you get. And we're going to be cutting a lot of sections. And a lot of times we're going to be cutting sections where there is a moment right here. See, when I drew this free body diagram, I did not put a moment right there. The reason I did not put a moment right there is because I cut the section at the hinge. If I had cut the section right here or somewhere else in the structure, there would be a moment. So, and then oftentimes we actually want to know what that moment is. So, beyond just the purely analytical concepts, we need to know what that moment is to be able to design the beam, to figure out whether the beam needs to be made out of steel or concrete or popsicle sticks and how deep it needs to be and all that jazz. So,
What kind of structures do civil engineers use that have like hinges in it?
that's a good question.
Like
So,
every day, like.
that's a good question. That's a fair question. So, admittedly, like, do we physically build hinges? Not so much. But do we still use hinges as an analytical tool for some analysis problems? You bet. So, I'll give you an example. One of the tools that we engineers use to this day is what's called an influence line. And we are going to learn how to do influence lines a little bit later in the semester. An influence line is a diagram that we use to assess structures that are subjected to loads that move. So when you have a structure and the loads move across the structure, that's what you use influence lines for. We can all probably guess what type of structure that would matter for, right? What type of structure do we design where the loads move? A bridge, right? Okay, so we will draw influence lines for internal shears. We will draw influence lines for internal moments, and so on and so forth. One of the tools that we use to draw the influence line for internal moments involves placing a hinge inside the structure. And so we look at the structure, look at how it deforms, and the resulting shape is the influence line. So while we might not be physically building, while we might not be physically creating hinges, we will use hinges for further analyses. So we do kind of need to know how they work. So.
But we never really use the ones that like move, right?
Not really, but I mean, we do have connections that are designed not to resist moments, like simple shear connections and things like that. Do we actually physically build hinges in structures? Not so much, but we do design connections where we assume they act that way because we assume they don't have any moment strength. So connections are where structures get really expensive. And so if you don't need a connection that resists moment, you won't put one in there because that's more bolts, more plates, more hole drilling, more time on the site, more money. So.
What material they made of is expensive?
Well, like if we're talking about steel, any connection just, it's a function of how many bolts that you put into it, right? So if you design a connection to resist shear and moment, that's more bolts, more time on the site. We will spend a great deal of time talking about that in steel design, about how to configure connections that are using either bolts or welds. So, did that get delivered?
DoorDash.
That got DoorDash to the classroom? They do that?
It's in the lobby.
I'm just, that's been, that, no, I'm okay. I guess I'm okay with it. That's just a first. DoorDash to the classroom. Next thing you know, they knock in, or they knock and they come in. I'll say, okay, you can deliver, but what's the reaction? Gonna look at me like, what are you talking about?
You like a buzzer for the door.
That involves electrical engineering. That's a lot of work. All right. Any questions about this? This is good stuff. I love this, by the way. We're gonna when we get into structures deflecting, we're gonna talk more about like how the configuration of a structure will affect its deformation. Like beams that are really deep deflect differently than beams that are slender. We'll have a lot of fun with that. What's that? We'll get to that later, but it involves shear deformations. So that's a later topic.
Okay.
That's a later
We're not
topic.
worried about that.
No. All right, real quick. One more homework on reactions, which is due Wednesday. I'm going to pull up the code one more time, but I'm going to give you a few minutes of your life back. Have a wonderful weekend. We'll see you on Wednesday. The homework's due Wednesday.